This is section 5.2 notes, and we have a warm-up. Graph the following and find the area from -4 to 4. Hint, this is the top half of a circle. So this is the top half of a circle from, not -6, from -4 to 4. This has a radius of 4. So here, we got here, and we got here. So that is very roughly the graph. And we're trying to find the area under the curve, which is a half a circle. So it's a half a circle with a radius of 4. So half of 16 is 8. So the area is 8 pi. This one, if we plug in positive values like 6 over 6, 6 divided by 6 is 1. So as long as we're plugging in positive values, it'll be 1. If we plug in negative values, that'll be 6 over -6. That's -1. So if we're plugging in negative values, the answer is always -1. So we want to graph the following and find the area from -4 to 4. So this area right here is actually a 4 by 1, but it's really -4 by 1. So this area is -4. And then from 0 to 4, this area is a 4 by 1. That's +4. So the answer, what is the area from -4 to 4, is 0. Now if it said the total area is 8. You'll be able to interpret the definite integral as the limit of a Riemann sum and express the limit of a Riemann sum in integral notation, as well as calculate definite integrals using areas. Let f be continuous on a to b, and let a to b be partitioned into n subintervals of equal length. Then the definite integral of f over ab is given by. All right, well, we have left endpoints for some rectangles. We have a midpoint. We have a off center, way off center. So it doesn't matter what points we pick for when we get to an infinite amount of rectangles. We just need the widest rectangle to keep getting split into smaller and smaller rectangles. Okay, I need to scroll down. Now we're going to take the limit as n approaches infinity. We're going to have an infinite number of rectangles. This is summation. K is going to go from 1 to how many rectangles there are. This is the function value. So that's actually the height of all of the rectangles. And this is the change in x. So this is the width of all of those rectangles. Now to convert that to integral notation, we have the integral from a to b, so a to b, integral from a to b, and that's an elongated s. Here's an s, and if we stretch that s out, we get the integral sign. So s stands for sum. Then the function, we have the function, that's the height of the rectangles, and instead of writing delta x, we usually write dx. So there's your limit notation to the integral notation. And we have lower limit of integration. We have upper limit of integration. This is the integral sign. This is the integrand, or the function we're integrating. And then our variable of integration is x. Now, you say that entire thing, integral of f from a to b. So here's an example. Write this as an integral. And they say we're going from -1 to 3. So there's the elongated s from -1 to 3. The function is 3x squared minus 2x plus 5. So 3x squared minus 2x plus 5, and the delta x is written as dx. Area under curve as a definite integral. If y equals f of x is non-negative and integrable over a closed interval a to b, then the area under the curve from a to b is the integral of f from a to b. So this is saying that this represents the area under the curve. Evaluate the integral. From -2 to 2, it's a half circle with a radius of 2. And so that's going to be 1/2 pi times 2 squared. Half of 4 is 2, so 2 pi. This evaluates to 2 pi because it's area under the curve. Area is negative when f of x is less than or equal to 0. which means that if you have area under the curve and area below the curve, this would be negative area. It's below the curve, or excuse me, below the x-axis. And this area would be positive because that is above the x-axis. We don't do accumulator functions. Constant function, the integral of a constant. Do I have an example? Yeah, it's right here. We're going to evaluate the integral of a constant. Let's do this with antiderivative. The derivative of 5x is 5, and we're evaluating from 3 to 7. Now, to get this answer, just take my word for it right now. We're going to plug 7 in. 7 times 5 is 35. It's always subtraction. And then we'll plug 3 in, which is 15. So the answer to this is 20. Evaluate the following integrals numerically. Use NINT. So in other words, use your calculator. All right, so that's actually math number 9. 8 is derivative, 9 is integral. And you see the integral sign. So we're going from -1 to 2, and it's x sine of x. There's the function, and this says with respect to x, and it just spits out an answer, 2.042. 2.042. Now the antiderivative of this, if we pull the 4 out, well that's the derivative of inverse tangent. So 4 times inverse tangent, and I've told you that you plug 1 in, and then you plug 0 in, but it's always minus. So we could do this right here. Inverse tangent of 0, like that. Well, the inverse tangent of 1 is pi over 4. In other words, what do we take the tangent of to get 1? Which is pi over 4, and inverse tangent of 0 is 0. So when I plug this in the calculator, I'm looking for an answer of 3.14159, or pi. Math number 9, we're going from 0 to 1. Of 4 divided by 1 plus x squared. There we go, there's pi. And finally, math number 9, we're going from 0 to 5 of e to the negative x squared. Whoops, I don't know where I got all that. Let's try that again. E to the negative x squared dx. So 0.886. Integrating a discontinuous function. The discontinuity is at 0, so this problem really suggests that we should integrate from -1 to 0 of the absolute value of x over x dx, and then we should integrate from 0 to 2, so we're skipping over the problem. We're skipping over the discontinuity at 0, because if you look at, we graphed this function in the very first slide. There's a jump discontinuity at 0. So here's the right side, that's 1. Here's the left side of 0, that's -1. So we're going from -1 to, let's go -1 to 0. That's a 1 by 1. That's actually a -1 by 1. That's -1. That is an area -1. And then 1 to 2 is an area of 2 by 1, area of 2. So 2 and then that -1, the area is 1, or the integral is 1. Now, your calculator should handle integrating over discontinuities pretty well. So -1 to 2 of absolute value of x divided by x, and we're looking for an answer of 1. And there's a little bit of a rounding error because of that jump discontinuity. It makes it a little tougher for the calculator to handle that. How about some homework? Integral from -7 to 5 of x squared minus 3x dx. There's writing that limit as integral notation. How about this limit notation? This is actually the function, and that's the height, and this is the base. Now, if we're cutting the base into n pieces, that means we're integrating from 0 to 2. And, you know, we would, how do we do this? We would, we'd plug in the first 2 over n into the function. So we'd have 1 plus this thing squared. And then we'd have the next 2 over n. And we'd have the function 1 plus this squared. And then we'd have the third and the fourth and the fifth and so on to however many rectangles we have. So the function is the square root of 1 plus x squared dx, because I'd plug in 2 over n every time. Now if you look at number 10, there's something missing. The 2 is missing. That 2 is not there. So when we plug 2 over n into this, the 2 is gone. So that means in the function there must be a 2 in the denominator. Now we're still cutting 2 into n pieces. We have the square root of 1 plus, and it must be x over 2 squared to get rid of the 2 every time we plug that in. Now this one, we're cutting 1 into n pieces, so we must be integrating from 0 to 1. And the function is cosine. We'd plug in 1 times 1 over n, then we'd plug in the second 1 over n, and we plug in the third 1 over n. But somehow we're getting this extra pi over 2. And we're plugging 1 over n in, so we're getting this extra pi over 2, so we better plug that in, pi over 2x dx. So since it's an extra thing that's happening, we better put that in there. Evaluate this integral. Well, we take the derivative of negative 20x is negative 20. 3 to 7 is negative 20 times 7 minus a negative 20 times 3. So that's negative 140 plus 60. So this answer is negative 80. Always subtract. Use the graph of the integrand and areas to evaluate. All right. So this has a y-intercept of 1, 2, 3, 4, and a slope of negative 2, so down 2 over 1, down 2 over 1. There's the line, and we're going from 1/2 to 3/2. Well, that right there, that is a trapezoid. So 1/2 times the height. The height is actually 1. From 1/2 to 3/2 is 2/2. That's 1. So the height is 1. Base 1 is what we get when we plug 1/2 in. So negative 2 times 1/2 plus 4, negative 1 plus 4, well that's 3. And then the height here is what we get when we plug 3/2 in. So negative 2 times 3/2 plus 4, that's negative 3 plus 4, so that's 1. So half of 4 is 2. So the answer to number 22 is 2. 24. Square root of 16 minus x squared is a circle, half of circle, with a radius of 4. But we're only integrating from negative 4 to 0, so it's a quarter of a circle. 1/4 pi times 4 squared, which is 16. So 24 is 4 pi. 26. Well, if we graph absolute value of x, it looks like this. If we turn that negative absolute value of x, that would be flipping that over, reflecting the graph over the x-axis, and then pushing all of this up 1. So that's the triangle that we want to find the area under the curve. Well, that's 1/2. The base is 2 and the height is 1. So the answer to 26 is 1.